Hello, welcome to section 6.1. This is going to be a pretty important section because the rest of chapter 6 is going to be kind of based on understanding the fundamentals of this section. It's about exponential functions. Exponential functions are in the news a lot nowadays with coronavirus going around because a lot of the time diseases actually spread in an exponential fashion. And we'll talk about that more after we see a few of these examples. But let's look at this first example 1 here. So we're given that a population of bacteria, there's initially 5 million bacteria. So it's starting with 5 million bacteria in it. And let's fill in the table and write a formula for f of t, the number of bacteria in millions, after t hours for each kind of growth. And for the first one, the number of bacteria increases by 5 million every hour. So it's initially 5 million bacteria, so that means after t equals 0 hours, there's 5 million. So we're going to let this be, it says in millions here, so 5 means 5 million. Okay, so and if it's increasing by 5 million bacteria every hour, then every time 1 hour goes by, this is just going to go up by 5. So this is going to be 10. 10 plus 5 is 15. 15 plus 5 is 20. Okay, so that's increasing by 5 million every hour. And how do you get a formula for this? Like f of t equals what? Well, this is linear because it's going up by the same amount every time. So for example, if you wanted to like plug in like t equals 3 into this, the way you would get f of 3 to calculate something to get that 20 is you'd say we're starting at 5 and then increasing by 5 3 times. So we could write this as 5 plus 5 times 3, which is 5 plus 15, which is 20. So in general, this is going to be 5 plus 5 times t. So that's the starting amount is that 5, and then the increasing by 5 million every hour is this 5 right here. Okay, so that's a linear function just like we looked at a lot in chapter 1. Now what if things are a little different? What if the number of bacteria doubles every hour? I want to point out this is something kind of more like the way bacteria actually work. Although a student in a biology major student in my last semester told me that bacteria can never actually double that fast because it just takes longer for cells to split. But if they could actually go this fast, this is kind of more like the way they work, because when bacteria have plenty of food, then every time they have enough food to grow, every single one of the bacteria might be able to split in 2. So it's not just going to be going up by the same number of bacteria. It's going to be doubling every certain amount of time. And in real life, they might be able to double every 5 hours or once every week or something like that. So anyways, let's fill in this table. So it's starting at 5 here, and then we're going to do 5 times 2 is going to be 5 times 2 is 10. So it doubled once in that hour. Then it gets multiplied by 2 again to become 20. Then it gets multiplied by 2 again to become 40. So that is doubling every hour. And you can see when it starts growing this way, it grows by 5 at first, and then it grows by 10, and then it grows by 20. So it actually ends up growing much faster than the linear growth after just a little bit. It starts off growing at about the same in the first hour, but then it grows by a lot more from hour 1 to hour 2, and then from hour 2 to hour 3. Okay, so now how do we get a formula for this? Well, let's see. Like, if we take this number 3 here, like, what can we do with the number 3? Like, if I wanted to do some arithmetic with that number 3 and get a result of 40, like, what is the arithmetic you can do to get that 40? Well, I'm going to look at it as we're doing 5, and then the 3 tells you how many times to take that 5 that you're starting with and multiply it by 2. So after 3 hours, it's 5 times 2 times 2 times 2. The 5 times 2 is 10, and then that times 2 is 20, and then that times 2 again is 40. So how can you write this as something with the 3 in it? Like, what is the arithmetic we're doing with that number 3? Well, that tells you how many copies of 2 to multiply together. So this is really 5 times 2 to the power 3. So in general, if you don't want to get the formula for f of t, it's that we're starting at 5, and then we're going to multiply by 2 once for every hour that goes by after hour 0, and t is the number of hours that go by after hour 0. So first I'm going to write it out with like repeated multiplication this way. With t factors of 2, and then we can write that out as an exponent. That's what 5 times 2 to the power t means. So there's your formula for f of t. Okay, so again, this is an example of a linear function, the first one. And we're going to see that this is an example of what we call an exponential function. And we'll have a more complete definition of that in a minute. Let's look at another example first. So an investor buys $1,000 worth of a risky stock and gets very lucky because the value grows quickly. So let's fill in the table and write a formula for v of t, which is a function that gives the value of the stock after t years, assuming each type of growth. So for each of these, let's fill in what we know, which is that it starts out at $1,000 worth after 0 years. So both of these are going to start with 1,000. So they have that in common. And then every year, these are going to grow in a different way. So the first one is increasing by $2,000 every year. So this should be going up by $2,000. So it starts at 1,000 and then goes up by $2,000. That's going to be $3,000. Woohoo! After 1 year, and then it goes up by $2,000 again. So that's going to become $5,000, and then it goes up by $2,000 again. And 5,000 plus 2,000 is going to be 7,000. Okay, so that's going up by $2,000 every year. Now, what if the value... Oh, actually, sorry, we forgot to make a formula for this. So let's see. If we want to get a formula for v of t, this is going to tell you what we can do with the input numbers to get these corresponding values. So for example, after 2 years, we're going to say it starts at 1,000 plus 2,000 2 times. So I'm going to start by writing this as 1,000 plus 2,000 plus 2,000 plus some other copies of 2,000. And the number of copies of 2,000 is the number of years that went by. So another way of saying 2,000 plus 2,000 plus 2,000 t different times, with t terms of 2,000, is v of t equals 1,000 plus 2,000 t. 2,000 times t means 2,000 plus 2,000 plus 2,000 t times. Okay. Now, let's look at the value of the stock when it triples every year. So if it starts at 1,000 and triples, 1,000 times 3 is going to be 3,000. And at this point, you notice that's the same as it was if it goes up by 2,000. 1,000 times 3 is the same thing as 1,000 plus 2,000. Now, what if it triples again? 3,000 times 3 is 9,000. And at this point, you'd realize, wait, tripling every year is better than adding 2,000, because this time it went up by a lot more than it did under the Part A scenario here. So 9,000 is way more than 5,000. And then what if it triples again? 9,000 times 3 is 27,000. Now we're really making money. So that is an extraordinary rate of return that you might be very lucky to get someday. But anyways, let's write a formula for this. How do you get these outputs using the number t here? Well, we're starting at 1,000, and then t, the number of years that have gone by, tells you how many times to multiply times 3. So we're going to take that 1,000 times 3 times 3 times some number of 3s. I don't know how many, so I'm going to write it as a dot, 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 with t different factors of 3. And how do you write 3 times 3 times 3 times 3 that many times? It's just 1,000 times 3 to the power t. And it's not a bad idea to check that this works. Is v of 3, let's say, is that equal to 27,000? Let's see. If we take this formula, do 1,000 times 3 to the power 3. Yeah, 3 to the power 3 means times 3 times 3 times 3, which is going to give you 1,000 times 27, which is 27,000. So this works. All right. So this is another example of comparing an exponential function and a linear function. And this is what happens with disease outbreaks, with epidemics, is that the rate that it grows, it's not like going up by the same number of infected people every week. What happens is the amount that it goes up by depends on how many people were infected the previous week. So it might increase by 10% or 20% or something like that every week. And that's 10% of what there was the previous week. So it's more like the amount gets multiplied every week rather than getting added by the same amount every week. And in real life, it's actually a lot more complicated than that, because it's not always going up by the same factor, because if people do interventions like social distancing orders and closing schools and all of that stuff, it might end up actually changing the amount that it goes up by. But anyways, that is an example of where if there was no other kinds of intervention, we would have exponential growth. Anyways, let's look at this formal definition of what is an exponential function. We say a function is exponential if it can be written in this form. Q equals f of t equals a times b to the power t, so, where a and b are constants and b is greater than 0. So let's see. The a in this case is 1,000. That's like the a we had. And the b in this case is that 3. So this is an example of an exponential function. The important thing is that the variable is the exponent of the thing. So let's look at some basic things about this. What is f of 0 here? Let's figure f of 0 out. So we're going to replace the t with 0. So we're going to get a times b to the power 0. What is b to the power 0? Well, let's remember back from the g.1, g.2 stuff, and also back in chapter 4, anything to the power 0 is 1. So hopefully you did okay in chapters G and 4. So you know that b to the power 0 is 1. So a times 1 is just a. So this is why it doesn't matter what b is. F of 0 is always going to be whatever a is. And that was true here too. In this case, v of 0, we can tell from the table, that is just 1,000. That's what it was supposed to be. That's like 0 copies of 3 being multiplied. So it's where it started at. So that's that. So that's called the initial value, the starting value of Q, or the starting value of f of t. Now, let's think. Let's look at this next thing. Every time t increases by 1, the output is multiplied by another factor of b. That's what's happening here. In this case, the b is 3, and every time t goes up by 1 here, you get another factor of 3 getting multiplied. So remember, a factor is just anything that you multiply, and in this case, it's describing how much it grows by. So we call b the growth factor. So those are some important terms we're going to be using a lot when describing exponential functions. Let's look at one more example here before we have some exercises to do. The exercises are pretty similar to what we've been doing. You're going to be given an exponential function, and it asks you to plug in some numbers into it. All right, so for a here, is this exponential? Is this written as a number multiplied by another number raised to the power of the variable? It is, yeah. So the a is 275, and the b is 3. So the initial value is what we're calling a here, and that's 275. That's what you'll get for q when you plug in t equals 0. The growth factor is 3. Okay, so that sounds good. How about this one? Is this written as a number multiplied by another number raised to the power of the variable? The important thing to check for is that the variable is in the exponent. And it is here. So, yes, this is exponential. The initial value is 80, and the growth factor is 1.05. Okay, so how about this one? So with this one, the variable is not the exponent. So the variable is the base, and the exponent is a constant number. So this is not exponential. This is what we studied in chapter 4. This is a power function. All right, so yeah, for exercises 1 and 2 and 3, I'll show the answers for those in the next video so you can check your answers. But make sure that you try it yourself. This is some important concepts to understand here, and the best way to do that is by doing it yourself. So anyways, I'll show you those answers in the next video so you can check.